Section 3.7 deals with related relates. This is really one of the first chances you get to see real world problems and how derivatives work in those. Remember that derivatives deal with slope, and slope is a rate of change or changes. And so generally what's happening in the real world is something is changing over time. And so we can do a lot of calculations with derivatives as we look at change over time. So we're going to look at an example first before we kind of jump in with math. So let's say we have a conical tank, a cone-shaped tank, and it's filled with water. And the water is being drained out of this. Okay, so maybe out of the bottom, the water's coming out of it. And this water is draining out over time. So that means the height is changing. As the water drains, the height changes. As the water drains, the volume changes. And as the water drains, the radius change. And they all change with respect to time, but they're all changing at different rates with respect to time. The height may be changing faster than the radius. So our original equation that we're going to deal with is just the volume of a cone. Okay, this is pi over 3 r squared h. So what we're going to do is we want to find how things are changing. Remember, rates of change, those are derivatives. So we are going to differentiate implicitly, but with respect to t. Normally when we've been distributing, we've been doing it in terms of x, but in this case, we want it in terms of t. So v equals pi over 3 r squared h. R and h are two different variables, so this is a product rule. So this is going to be r1, and this is going to be r2. Okay, so we're going to take the derivative of v. So we're doing the derivative of v with respect to time. Okay, and I know you guys asked last week or the week before why we use the dy dx. This is why, because we don't always differentiate with respect to x. Sometimes we do it with respect to time, and we need to be able to say that. So that's why this notation is nice. Okay, so dv dt, we're doing the product rule. So we have 1 pi over 3 r squared. d2, we need the derivative of h, which is just 1, but then remember we don't know what h is. It's some sort of function with respect to time, so it is dh dt. So that's 1 d2. Plus 2, that's h. d1, we have pi over 3, and r squared, we're going to bring the 2 down, lower the exponent, so we have 2r. Then we need to apply the chain rule. We don't know what r is necessarily, so we're taking it with respect to time. So we have dr dt. Okay, since we're differentiating with respect to time on both of our variables, h and r, we need the dr dt or the dh dt. So this is our derivative. This is our change in volume over time is this formula. There's not a whole lot to do with this other than they have a pi over 3 in common, so I'm going to factor that out. So we have pi over 3 r squared dh dt plus we took the pi over 3 out, so 2 hr dr dt. Okay, so that is our expression for dv dt, change in volume with respect to time. We are going to use that in just a second. Okay. The height of the water, okay, so we're draining water out of this cone. The height is changing at a rate of negative 0.2 feet per minute. The radius is changing at a rate of negative 0.1 feet per minute. We want to know how fast is the volume changing when the radius is 1 and the height is 2. Okay, so let's take a look at what we have here. The water level, the height is changing at this. So our height is changing with respect to time. Our dh dt is negative 0.2. The radius is changing at this rate. So our dr dt is negative 0.1. And we want to find the rate of change in the volume. So what we're trying to find, the rate of change in the volume. We are trying to find dv dt, the change in the volume over time. Sorry about that, got a little out of control there. when the radius is 1 and the height is 2. So we're going back to this equation. Let me see if I can move this down so we can actually use it. Not like that. Oh, there we go. Nope, nope. We can do it, I promise. This one. There we go. All right, there it is. Okay, so we want to find dv dt when all these other things are happening. So dv dt equals pi over 3. R is 1, so we have 1 squared. dh dt is negative 0.2 plus 2hr. Let's see, h is 2 feet. R, we already said, is 1. And this is dr dt, which is right here, negative 0.1. Okay. So dv dt is pi over 3. Let's see, that's negative 0.2 plus negative 0.4. You can just put that in your calculator. It's not really necessary to do by hand. So that's going to be negative 0.6 times pi over 3. And when we do that, we get negative 0.63. We need to think about our units for this. So this is telling us how fast the volume is changing. We're talking about feet. Our volume is in cubic feet. And all of our time was, let's go back and look at time. I think it was minutes, but I want to double check. Yep, feet per minute. All of our time is measured in minutes. Okay. So our volume is changing at negative 0.63 cubic feet per minute. That's the rate the volume is coming out of this tank. Okay, so these are the type of equations we are going to be working with. Before we get into more complicated ones, I want to show you a super easy one. So here it is. Here's just a very basic equation. We have y equals x squared plus 3. Okay, we know that's a parabola, shifted up 3. And we want to find dy dt. So how is y changing over time? So I want you to imagine that, like, on this parabola, we have some sort of particle that's moving with respect to time. So you have kind of another variable in there. So we want to find dy dt when x is 1, given that dx dt equals 2 when x is 1. So what we're going to do first is they want us to find dy dt. So we need to take the derivative of this thing with respect to time. So y equals x squared plus 3. We're taking the derivative of this. The derivative of y with respect to time. Let's see, the derivative of y is just 1. But we need 1 dy, and instead of x, we're not doing dy dx, we're doing it with respect to time. So dy dt equals, we need to take the derivative of x squared, so that's going to be 2x. But then again, this is with respect to time, so then dx dt plus 3. The derivative of 3 is still 0, and we can just leave it at that. Okay, so this is our derivative with respect to time. The problem was asking us to find dy dt, so that's what we want to know. Dy dt when x equals 1, so we're going to plug in 1 for x, given that dx dt equals 2. So when we do that all, which is also super easy, dy dt equals 2 times 1 times 2 is 4. Okay, so our y is changing at a rate of 4. Okay, on the next page we're going to do some more practical. In the next video we're going to do some more practical examples of these.